Assalamu alaikum. In this video, we are going to discuss the laws of probability, which allow events to be combined with each other and the probabilities of the new events we compute. Probability laws define the rules for relationships between events. There are four fundamental laws that we will be discussing: law of complement, of union or addition, of intersection or multiplication, and the law of total probability. Events can be combined and the probabilities can be calculated using these laws. The simplest of these rules is the law of complement. The complement of an event A is defined as denoted as A bar or A dash sometimes. It is equal to the sample space minus that event, where S is the sample space. So the event A complement is going to have all of the simple events which are there in sample space, but not in the event A. It is just like taking the difference of between two sets, where the first set is the sample space and the other set is the event A. The law of complement states that the probability of A complement is equal to the probability of the sample space, which we know is 1, minus the probability of event A. So eventually, for any event for which we need to find out the complement of, the probability of this event is going, the complement of this event is going to be 1 minus the probability of that event. We can have these two additional notations to represent the complement events. Complements of an event include all simple events that are in S but not in A, and this can be modeled using this Venn diagram. So you see a sample space which has all the possible outcomes in it, event A which constitutes upon some of those simple events, and A dash, or the complement of this event A, is all of the other simple events in sample space except for those that are there in A. Let's see this with an example. The probability that a student will pass the probability in statistics course is 0.8. What is the probability that the next student enrolling in the course will get an F? So a probability of F is the same as saying that the probability of P complement, that a pass complement, that the student will not pass the course. Since we know the probability of the student passing the course is 0.8, we can use the law of complement to find the probability of this event, which is pass complement. So the probability of pass complement is 1 minus probability of pass, which is 1 minus 0.8 is equal to 0.2. So we can say that there's a 20% chance that the student enrolling in this course next will not be able to pass it. Another example asks that what is the probability that a randomly drawn card from a deck will not be an ace? We know that there are 52 cards in a deck of cards, and there are 4 aces. So the probability of finding an ace is 4 by 52. And now, in order to find the probability of not finding an A if you randomly pick a card is the complement of this event. And by using the loss of complement, we can have probability of not having an ace when we draw a card randomly from the deck is going to be 1 minus P of ace, because it is P of ace complement, and which is 1 minus 4 over 52, 92.3%. So you can express probabilities as percentages or as the fractional values. The second law is the law of union, which defines the rules for how two events can be combined to form a bigger event. So two events can be united to form a bigger event with the elements of both contained in that event. This is also known as law of addition because the probabilities of the events are added. This can be modeled using a Venn diagram as shown on the screen. So we have two events on this sample space S. Event A and event B have some overlapping area, which essentially means that there would be some simple events which are there in A and in B both. This can be modeled using a Venn diagram as shown on the screen. So here we can see that there are two events on the sample space S, A and B, and there is some overlapping area between A and B. This essentially means that there would be a few simple events of the sample space which are in both A and B. So now, if we want to compute a new event which contains the elements from both A and B, in other words, if you want to find out the union of these two events A and B, we can use that. You do that using the law. This can be modeled using a Venn diagram as shown on the screen. So here we can see that there are two events A and B on the same sample space, and we can also see some area of the sample space, which is shared by both A and B. So this is an overlapping area between A and B. And this is the joint probability of A and B. By joint probability, we mean that this area is corresponding to the intersection of these two events. It is the probability that both of these events will occur together. Now, in order to compute a new event, which is the union of these two events, it actually means that we are adding elements from A and B to make a bigger event, which has all of those simple events which are there in A and in B. But if we look at the diagram, we can see that simply adding the probabilities of A and B um, results in this area, overlapping area, being added up twice. So here we see P of A, unit P of B is P of A plus P of B. And if we just leave it to this point, it is going to be including this area twice because P of A includes this area and P of B also includes this area. So what we do is we subtract this joint probability or this intersection area from this expression in order to get this being added only once. So the law of union lets two events be combined, and the probability of the new event is calculated using addition of the two events minus the probability of the intersection of those two events, which is the probability of joint occurrence of those events. See this with the help of an example. A factory installed two power backup systems to ensure continuous power supply in case of outages. The probability that the backup systems will generate an error is 0.2 and 0.17 respectively. The probability that both generate error is 0.09. Now we're required to find out the probability of this event that at least one of the system will generate an error. We define event A as this event that system 1 generates error and B as the event of system 2 generating error. Now we need to find out the probability that at least one of the system will generate error, which corresponds to A union B. So the probability of A union B can be found with the help of law of addition. P of A union B is P of A plus P of B minus P of AB. Probability of A is 0.2, probability of B is 0.17, and the joint probability of A and B, which corresponds to the event that both of the systems generate error, is 0.09 as given in the data. So now the probability of A union B, or the event that at least one of the systems will generate an error, is 0.2 plus 0.17 minus 0.09, which gives us 0.28. So there's a 28% probability that at least one of the systems will generate an error. Now for the second question, which is none of the system generates an error, that in case of outage, both of the systems will work. So in order to calculate that, we can make use of the law of complement. We have already calculated the probability for the event that at least one of the system generates an error. So the complement of this is that none of the system generates an error. So in order to find out the probability of this event that none of the system generates an error, we can employ the law of complement. So P of A union B whole complement can give us this probability, which is 1 minus 0.28 is equal to 0.72. So there is a 72% chance that both of the systems will work. Consider another example. Students utilize the summer semester to clear their pending courses. Two courses, ACP and Math, will be offered in summer 2024. 63% of the students have shown interest in ACP, 34 in Math, and 27 in both of them. What is the percentage of students who wish to enroll in at least one of these courses? So from the data given, we know that probability of MAD is 0.34, probability of ACP is 0.63. And by the way, the percentages give the probability. These are the proportion of the whole from the 100%, which are equivalent to the probabilities of these events. Probability of ACP is 0.63. Now we need to find out the probability of the proportion of the students enrolling in at least one of them. For that, we also need to know the probability of both of these events happening together, which is the joint probability, and which is also given in the question. So probability of MAD and ACP intersection between them is 0.27. Now, in order to find out the probability of the proportion of students enrolling in at least one of these courses can be computed using the law of addition. So probability of MAD plus probability of ACP minus the joint probability of MAD and ACP. 0.34 plus 0.63 minus 0.27 gives us 0.7. So 70% of the students will enroll in at least one of the courses. And we can also find out the proportion of the students who do not appear in any of the courses, which is very clear from what we have computed now. It is 30% of the students, they will not enroll in any of these courses. Here's another example. The survey was conducted over 40 students, including 20 girls, asking their preferences of courses among programming, mathematics, social sciences. 22 students preferred programming, 6 of whom were girls. 14, including 10 girls, preferred mathematics. None of the boys preferred social sciences. What is the probability that a randomly selected student is either a girl or they have preferred mathematics? So now there's quite a few different events being mentioned in this question, and we need to build a table to represent all of these events and their proportions or probabilities. So we can create this two-way contingency where, since we are dealing with two qualitative attributes, one is the preference for a course and the other one is gender. So we plot gender in rows and the preference for courses in the columns. Here we have three columns because we have three values for the courses: programming, mathematics, and social sciences. And gender, for gender, we have girls and boys. And these are the marginals. Um, from this, the data given in the question, we can fill in the value. So we know that the total number of students is 40. We fill this value. 20 girls. So we can fill in this value, which is 20 girls, which leaves out of 40, if 20 are girls, then we know for sure that the other 20, they are boys. Now it says that 22 students preferred programming courses, and this is the marginal. This is the total for programming. So we put it in this marginal column. This is 22 of the total students they preferred programming, and 6 of whom were girls. So now we know that out of these 22, 6 students who preferred programming were girls. So we put a 6 here. Naturally, the remaining students are boys. So we put a 16 here because we need to have these values summed up to this total. Then it says 14, including 10 girls preferred mathematics. So a total of 14 people preferred mathematics, out of whom 10 were girls. This leaves only 4 being boys who preferred mathematics. None of the boys preferred social sciences, so we have a 0 here. And the remaining 4 students, because now if we add these values, we get 36, and only 4 students are left. So we know that only 4 students out of the 40 total strength preferred social sciences. And we also know that none of those were boys. So we put a 0. This leaves 4 in this cell. So now when we have all of these values filled up, we can calculate the probabilities. The question asks us to find the probability that a randomly selected student is either a girl or they have preferred mathematics. For this event, this is a union between the event of a person being girl and the event of them having selected mathematics. So this is equal to probability of being girl plus probability of being preferring mathematics minus the probability, the joint probability of being a girl and preferring mathematics. We can get these values from the table. So the probability of being a girl can be found out from here. We know that 20 out of 40 are the girl. So this is this we put here. Then we also know that the probability of preferring mathematics is 14 out of 40. So we put this value here. And the joint probability of being a girl and preferring mathematics is given in this column, which is 10 by 40. So we apply this probability law of addition and compute the values, which gives us 24 over 40, which is 0.6. So 60%, there is a 60% chance that a randomly picked student is either a girl or they have preferred mathematics. Now, it is the law of intersection of two events. When two events have things in common, we can compute intersection. And if they do not have anything in common, the intersection is going to be 5. Those events are known as disjoint events. The intersection contains the simple events common in both events. It also specifies the joint probability of two events, and by joint probability, we mean the event of both of those independent individual events happening together. It raining outside and the temperature dropping below 40, before 4 degrees. So these are two different events, and if they happen together, the probability of this new event, this which we call as the joint probability of these events, can be calculated using the law of intersection. But we need to know some principles that guide for the application of law of intersection. So this is an example of what is meant by the joint probability, being a girl and securing above 80% marks. And even in the previous example, we've seen that being a girl and preferring mathematics for the course selection was also an example of a joint probability. This can be calculated with the law of multiplication. For example, rolling a die and recording the value. If this is an experiment, we know that the sample space is 1, 2, 3, 4, 5, and 6. Now, if we have this event and odd value, we have the simple events 1, 3, and 5 coming into this event. And for event B, which is a value above 4, we have only two simple events um, in the outcomes of for event A. Now, A intersection B, if we apply the intersection rules as we do on sets, we get 5, only one element from the sample space added to this intersection. And now we can compute the probability. Since each of these simple events is equally likely, we get P of A intersection B as 1 over 6. Now there is a concept of independent events because before we can apply the law of multiplication or the law of intersection, we need to know what independent events are. If the outcome of an event doesn't affect the outcome of another event, we say that these events are independent of each other and they do not interfere with the probabilities of each other. So if A and B are independent events, only in the case when the probability of A remains same whether or not B has occurred. So for example, your friend eating a burger will have no effect on your grade the next quiz. These two events are independent. And when the events are independent, the joint probability is simply the product between the probabilities of the two independent events. So P of AB or P of A intersection B, it can be written both ways. You can write it as P of AB, or you can write it as P of A intersection B using the intersection symbol, is equal to P of A multiplied by P of B. But there is another type of events in which the probability of one event, the occurrence of one event, influences the probability of another. Say, for example, if you say, if someone asks you what's the probability of rain, you may take a peek outside and say, since it's a irregular day, the probability of rain is only 60% or 30%. But if someone tells you that it's being cloudy outside, now the probability of rain will increase. So it being cloudy outside has an influence on the probability of it raining afterwards. In this case, these events are not independent. The probability of it raining is not independent of it being cloudy outside. The outcome of one event influences the outcome of another event. Event A is dependent on B if the occurrence of B changes the probability of A. The probability of we have already seen the probability of rain will increase if it becomes cloudy. So in this case, probability of A intersection B or probability of A B cannot be computed directly using this expression which we have just seen. But how do we do it? For this, we need to know some more um, additional things about events, and then we will be able to calculate this probability, joint probability when the events are dependent. Consider this example. A bag contains 20 balls with 4, 5, 7, 3, and 1 balls of colors red, blue, green, yellow, and pink respectively. Two balls are drawn with replacement. What is the probability that both balls are green? Now, when we draw a sample or something out of a hole with replacement, it means that we draw it once, make the observation, and then put the item back into the bag. So next time when we draw another item, the bag or whatever hole we're drawing it from is back to its initial state. In this case, the successive drawings are independent events because the probability of drawing a red, green, blue, or whatever color balls are there is not going to change between the successive drawing. It's going to be the same for the first draw. It's going to be the same for the second, third, and fourth when you do it with replacement. So drawing with replacement means that the item drawn is noted and then put back into the collection. The same item can be drawn again on the next draw, and we do not have the probabilities changed between these successive draws. Event A is defined as the first ball is green. Event B is that second ball is green. And now we need to find out the probability of what is the probability that both of the balls are green. So P of A is 7 by 20 because each of the drawing any of these balls is equally likely, and we have 7 of the balls which are green. So 7 by 20 is the probability for drawing the first ball as green ball. And now after drawing this ball, noting the color, we put it back. So now again in the bag, the number of 7 of green balls is 7 again. So P of B is again 7 by 20. Since these events are independent, the event that the ball was green, which was event A, the first ball was green, has no effect on the probability uh, of the second ball being green. So in this case, if the events are independent, and we can calculate the probability simply by multiplying their irrespective probabilities. And we get 14 by 400, which is 0.035, only 3.5% chance that both the balls drawn with replacement would be green. Another concept is of mutually exclusive events, which have no outcome in common. These events are also known as disjoint sets. So in case of events A and B being disjoint, A intersection B is going to be a null set or phi, and the probability of A intersection B is going to be 0 because they have nothing in common. And the joint probability is going to be 0. This can be explained with the help of a Venn diagram. We can see mutually exclusive events which have nothing in common, and below the diagram below shows non-mutually exclusive events, the events in which there is an overlapping area. So in this case, the intersection of those two events is not a null set, and the probability of these events is not a 0. When you have mutually exclusive or disjoint events, the union of these events is simply addition of the two probabilities of these events. Because in this case, the P intersection A, probability of P intersection A becomes 0. So you're left with only two values being added, P of A plus P of B. An event and its complement are always mutually exclusive. So intersection between between A and its complement is always going to be a null set, and the probability of this event is going to be 0. Now let's do an example of drawing without replacement. A bag contains 15 balls, including 3 blue, 2 green, 4 yellow, and 6 pink. Two balls are drawn one after the other without replacement. So when it is without replacement, we know that the first ball which is drawn goes out of the bag, and the probabilities of the remaining balls they change. What is the probability of the second ball being pink if the first ball is here? So here we define event A as the first ball is yellow, event B, the second ball being pink. Now the probability of A, because all of the balls are still there in the bag, when we are drawing the first ball, the probability of it being yellow is depends upon the initial number of balls in the bag. So we had 4 yellow balls, and the total of 15. The probability of drawing the first ball as yellow ball is 4 by 15. But once this ball is drawn, now the remaining balls in the bag are only 14. And out of those, the remaining balls include only 3 yellow balls, and the rest of the counts are the same. But because of the total count of the balls now coming down to 14, the probability of observing a pink ball on the second draw is now only 16 over 14. The probability of drawing a pink ball initially was 6 by 15 when they were all of the 15 balls in the bag. But after the first draw, now the remaining balls are only 14. So now the probability is 6 by 14. We're going to continue doing this concept in the next video also. This concept forms the basis of the conditional probability that we're going to study in the next video.